Hey everyone. Um, I didn't get this is Anant from PTS. I didn't get to go over the second problem from Homework 8 really thoroughly during our recording session, so this is just a little um, like more deep dive into that problem. So let's get started. Um, yeah. So the first thing that we will have to do is let's look at the question first. Let's see what are all the important parts that we need from this question. So the first thing you can see is that we have a bunch of givens here. We have the cross-sectional area of the water. We have the velocity of the water coming out of the cart. We have the mass of the water, area of the copper, the density of the copper. We also have the density of the water. But yeah, and then let's go over to the actual text. So the first thing that I want to go over is in the first paragraph. So the first thing is that there is an inertial frame or a reference frame to the ground, and that's the V prime. And that's what's denoted by the V prime. And then we also have two other frames. One is the accelerating frame that follows the cart through its motion. And then we have a uniformly moving frame. And I'll explain what each of those do in a second. But then the last thing to look at here is that we have these two formula, which basically relate the accelerating frame and the constant velocity frame, or make it as a function of the inertial frame. And then again, inertial frame is that nothing is moving, you just see the cart move. The next thing you want to see is that the back end of the cart is A prime. The so we have a given the area of the water, and then we have the velocity of the water coming out of the back with respect to the accelerating frame, and that's denoted by this v tilde. So from when you're looking at the cart itself, when you're following the cart through its journey, the water that's coming out of that is going at a constant speed, and you can also ignore gravity, which means that the water will be always at a it'll always be horizontal, so you don't have to worry about it like dipping down or anything like that. And yeah, and then afterwards you get to a place where they basically derive a few equations the um related to the uh velocity of the column of water that's coming out, and that's going to be an important thing later on. So we have this equation, which basically says that the velocity of the column at x naught and our x equals 0 and at the initial time step, at the initial time is equal to the negative magnitude of the velocity of the water. Okay, so that's the main things from this section. And then we also have, and now the density of the water as a given. We also have density of the copper, area of the copper, and then an important thing is that this mass of the copper is increasing as a function of time. And I think it says somewhere in the beginning that the mass of the water in the cart is decreasing as a function of time, which makes sense because the copper is getting added to the cart and the water is getting shot out of the cart. And then the rest of this paragraph, like from like here to here, is all just different assumptions. You basically don't have to think about a lot of things related to the mass of the copper. Just know that it's stationary outside of the cart and it's adding mass to the cart. And then afterwards, we want to also look at things to do at the. Oh, the first thing is that answer the questions using the inertial frame, and that'll come in handy for a few equations that we have to use. And then at time equals 0, the left side of the cart is at x is equal to 0. And then at the right side of the control volume is x equals to L. So this isn't so if we go back to the photo, this isn't at the edge of the cart, but it's somewhere outside of the area of the cart. And this photo makes it look a little bit confusing, but when we get to that part of the momentum section, I'll explain that a little bit better of what that L, where that L actually winds up being. And then the other thing that you got to see is that the right side of the cart is B prime of t, and then over here the left side of the cart is A prime of t. Yeah. So that's the main things to get take away from the actual problem. And now we can go over to the questions. So the first thing I want to quickly do is summarize what we need to know for this. So a few different things. The first thing is that we have 3 reference frames. The first one is an inertial frame. This does not move. And this is denoted by V prime. Second one is that there is an accelerating frame. And this moves with the cart. And so this is the most intuitive one because you're just basically following the cart around. And this is V tilde. And the last one is a slightly weird one that we're introduced to is the constant velocity frame. And this moves at a speed. V is equal to the velocity of the cart in the inertial frame at time 0. And that's given. So that's the main things we need to think about. So when I think someone during the actual session asked a question, when do we use each of these 3 frames, or how do we know when to use it? So the main the main thing that we want to realize is that the problem asks us to get everything in the inertial frame. So that's the basic frame that we should be getting all our answers in. The accelerating frame is convenient in at least the first 2 parts of the problem, where it's more intuitive to think about how mass is exiting and entering the cart rather than seeing how the cart moves and the mass like moves with exits and enters with that. So it's just a little bit more of a simplified domain. And the last one, basically we have an equation here, and this equation will come in handy for doing a lot of momentum calculations. So that's basically the only reason we need this constant velocity frame. Okay, so for the first part of the question, or the first for A. So we have the question is, let the mass of the water in the bottom of the cart at time 0 be mw is equal to mw is 0. So we just have an initial condition at time equals 0. Find the mass of the water as a function of time. Okay, so the first thing we should think about is what are our givens. So we know that right now we have this velocity of the water in the inertial frame that's given to us. So what we can do is now let's think about this, since we're given it in the not the inertial frame, sorry, the accelerating frame. Since we're this is given to us in the accelerating frame, let's think about the equations in that frame. And that works because the way that the mass of the water is not going to change in these different frames, and that's going to stay constant. So we can use this frame and do all of the equations. So let's look at our general mass conservation first. So we have the derivative of m, I'm going to just denote it as mw for the mass of the water, dt is equal to rho w, aw, and this is the mass flow out of the system. And all these 3 are constants, we could say. Constant. So now what do we do? Now that we have this rate, we can integrate. And when we integrate, we get mw of t is equal to negative rho w, aw, oh, sorry. Times t plus c. And then since it's a constant, that's why you can just multiply by t and then you just add a constant at the end. And then we also know at t is equal to 0, mw is equal to 0. So what this means is that our final equation for the mass of the water at time t is equal to First, the initial constant, so mw at 0 minus rho w, area w, v tilde w times t. Okay, so this is our first answer. That was pretty straightforward. You just integrated a constant and you got that answer. Now for the second part. Yeah, that's fine. Now for the second part. So we have part B. Now we're looking at the mass, the same thing, but for the mass of the copper. So we're again given that the initial condition at a time 0, we have the mass of the copper of 0, and we need to find the mass of the copper as a function of time. And we're also given the information that we're allowed to express this in terms of the unknown velocity v prime, which is the velocity of the card in the inertial frame. And now let's go through this. So the first thing we do is, again, we used the accelerating frame last time. So let's see if we can use that to at least start with a simplified equation. So we have d, I'm going to call this m cop for copper. dt is equal to negative a cop rho cop v prime or v tilde cop. But the issue is that this term here is an unknown. And so we don't know what that term is. So we have to now put that in terms of something else in order to get something in terms of our knowns. And we got a hint. We got a hint that we're supposed to put our answer in terms of the velocity of the card in the inertial frame. So let's try to convert this v copper into its inertial frame equivalent. So if we just write v copper here, and this comes from these equations over here, we can write this in terms of what is this? V copper t in the inertial frame minus v prime of the cart in the inertial frame. Okay, and then this, it'll be 0 because the copper does not move in the inertial frame. So that's 0. So what this basically gives us is, I'm just gonna write it over here. V cop is equal to negative v prime cart of t. And that's something that we actually do have as a given. Or that's something we're allowed to use in this case. So now let's take our equation d of m cop et, and let's substitute our new value, a cop, rho cop, and v prime cart of t. And now this, we should now realize, unlike the part A, this is not a constant. So, and we don't know the expression for this thing, so we have to leave it as an integral. And the way we do that, so let's first integrate both sides. Integrate. And this will leave us with m cop as a function of time is equal to, so we're integrating from 0 to t of a cop, rho cop, v prime of the cart as a function of t, or in this case, we're going to use a dummy variable t prime because we use t as one of the integral bounds, and then dt double prime, and then plus c because there's a constant, and this is technically a definite integral. And then we know this constant because at t equals 0, this entire integral will disappear. So this c is simply, c is equal to m cop of 0. Okay. And that's basically the entire thing. We can also remove this a and rho out of the equation, or out of the integral, because they're constants. So you basically get m cop t is equal to a cop rho cop 0 to t of v prime of the cart with these little dummy variables plus m cop 0. Okay, so that is our the answer to our second, to part B. So now let's go to part C. This one is the part that's really confusing because of the weird derivatives and the bounds of these integrals. So let's first look at the easy ones. So if we go back to the question, we see that um, we have four things that we need to find. So the basic equation is write down, just highlight that, write down the expressions for the momentum due to four things. And the four things are the water exiting behind the pump. So again, we're looking at the inertial reference frame. So whenever the water is being ejected from the cart, that is still within the domain of the inertial reference frame. So that still has a momentum contribution because the mass of that water is increasing as it exits the cart, or the amount of water is increasing. So the mass increases, which will increase the momentum. And then we have the water in the cart. So again, within the cart, the overall mass of the water in the cart is decreasing. That'll also cause a change in momentum. Then the same thing with the copper wire. The amount of copper wire on the cart is increasing. That'll cause a change of momentum. And lastly, the amount of copper that's outside of the cart, but still within the inertial reference frame or in the domain, is decreasing. And that may or may not cause a change in the momentum. So we have to look at all four of those. Let's first go to 2 and 3 because they're the easiest. So this is looking at the momentum of the, oh, sorry. This is looking at the momentum of the removal of the water from the cart. So let's look at that first. So the basic equation is mass of the water in the cart times the velocity of the cart, because this tank of water is moving at the same rate as the cart itself, and we are in the inertial reference frame. So then this is the first part of it. That's basically what the momentum is. Now, if we take the time derivative of this thing, so this is, I think, Ci, and I'm just going to say di or dii. That's fine. And then dii is the derivative of this thing. So ddt of mw v prime of the cart time t. This is just a basic product rule, and you get m dot w v prime of the cart at time t plus mw v the derivative of the cart velocity. That was cart at time t. Okay, and now this equation and this expression are known because we got that from the first part over here. So if we just substitute those inside of there, we can get the final expression for the time derivative of the momentum, this is just basically just plugging and chugging from part A. T plus mass of the water in the cart, O minus T water, rho water. And then fill times the cart. Okay, so that's the equation for that. That's the second one done. Now let's go to the third one. So let's go with 3. Same thing for 3. So we first have the mass of the copper times the velocity of the cart at time t, which is the momentum because again the big bundle of copper is moving with the cart in the inertial reference frame. Now we take the derivative, we just do a nice ddt of this. We get m dot copper v prime of the cart at t, and then again product rule, so we get m of the copper v dot prime of the cart at t. Again, same thing from part B. We know those two expressions. So we can now just write that down as area of the copper, density of the copper, V prime cart squared plus the integral of the velocity of the cart. That's the dummy variable, and then multiplied by the rate of velocity change of the cart. Okay, so that's number 3. Now we get to the interesting parts or the harder parts. So the first thing we're going to do is let's tackle 1. So what 1 is basically saying is that let's say we have x equals 0 here, and we have our cart. It's got its little copper bundle, and it's got the little spout which shoots water out. Now, and this part of the cart is AFT, which is important. So let's say this is time t is equal to 0, or like 0-ish, so 0.5 or something like that. So right now, the amount of water that's come out is L1, let's say. But at a separate time, we'll also have the same cart. This is again, x is equal to 0, but it's going to go forward some amount. To go forward, it's going to, it's going to shoot this much water out. And then again, it's going to keep being like horizontal because we're not thinking about gravity right now. So then we go L2, let's say. And then again, AFT is where this cart is. So as you can see, L2 is greater than L1. And then if you just look at it just as an image, you know that the volume of the water in the second one is greater than the volume of the ejected water in the first one. So that's where the change of momentum is going to come from. So let's just suppose, and will help with our integral, or make sense of why our integral is the way it is. Let's suppose that V prime of the column, because that's what we're looking at, this column of water, was constant. How would our integral look? How would our momentum look? So we would have m of x, before we confuse that with the mass, is equal to the density of the water times the cross-sectional area of the column of water times the length of that column of water, because this will give us the mass, times the velocity of the column in the inertial frame. This would be what the momentum looks like in the inertial frame. But this is not constant. It is a function of x. So whenever this moves a little bit, this velocity changes. Whenever it moves a little bit more, the velocity will keep changing. So we have to integrate. So what does that look like? And that'll look like what you see in the solutions, where you have rho w, aw from 0, from the left side of the domain all the way to the start of the cart, because that's how big the column of water is. So AFT of the velocity of the column of water at x of t prime. Yeah. So now we have to, so this is the this is the this is for CI. This is the answer for that one. But now we have to take the time derivative. And that's where this equation up here comes from. So delete that quickly. So right now, this is an interesting integral because the bounds of the integral depend on time. So when you take the time derivative, it's not as the simple thing like the fundamental theorem of calculus. So you have to do this equation basically. So this is in terms of d dx, but it's the same thing if we just change it to d dt and we're just basically swapping the x's and the t's and all these functions. So what this basically will do is we can first of all remove rho w a w from this because they're constant, and then we take d dt of 0 to a of t, b prime of the column velocity x prime. And then, so this, I'm putting some parentheses because just this part is equating to everything else, and it's all multiplied by rho WAW. So this will equal, so the first thing we have to do is we evaluate the function at the top integrand, and we multiply it by the derivative of the top integrand with respect to, in this case, time. So the first thing we'll do is we'll evaluate the inside of it at a of t, comma t. We'll multiply this by dA dt, and this is just, since this is the left side, this is how much the cart moves. This is just the velocity of the cart with respect to time. Then we have to add. So then what happens? So then, well, we should do the same thing on the bottom integral, or the bottom bound of the integral. But we realize that this is just going to be 0. It's not going to change at all. So this entire derivative will just go to 0. We don't need to think about that. And the last thing we need to do is we just need to take the derivative of the inside of the integral. So when we add that in. So that would become 0 to a of t of the derivative of the v column dt dx prime. Okay, and at this point, the solutions ended up substituting in the constant velocity frame, but I think it'll make a little more sense if it'll simplify things if we just do a little later on. So once we get this thing, this is probably what looks familiar from the solutions. So now what we have to do is, it's still saying the problem, but we have to evaluate this at time t equals 0, where a prime of t naught is equal to 0. So it just starts at the left side of the domain at t equals 0 is what that means. So what ends up happening is that you would evaluate this integral from 0 to, this would be 0. So then this entire term will just go away because you're evaluating from 0 to 0, which means that your final equation would then turn out to be rho w a w v prime cart at t naught, because you're evaluating the velocity at t naught times velocity of the column at x equals 0 and t naught. So now again, this value is unknown to us. But what we do know is that this should be familiar, because in our givens over here, we know that the velocity of the column at again 0 and t naught, which is what we had over in our equation, is equal to negative of the magnitude of the velocity, the water velocity, which is given to us. So what we have to do is we need to somehow convert what we have in. We should get it in the moving reference frame so that we can finally put it in terms of this given quantity. So what we'll end up doing is we can say this is from the original equations where it converts from the inertial frame to the moving frame on the first page of the assignment. This is just rearranging that. We can get we'll get this. So we'll get this as a function of v prime card at t naught, and this is something that we've been using throughout the question. And then we have this oh, this column, yeah, this column. Then we have this in the moving reference frame. So now we can now substitute the moving reference frame value for what we originally had, and then that'll be rho w a w prime cart at t naught b column 0 t naught for b prime cart at t naught. Okay, and then this is just equal to rho w a w v prime cart, and then, well, we know, so we got the cart, this is fine, and then we know that this term over here will be the negative of the velocity of the water in the accelerating time, the accelerating reference frame. So that is the answer to this one. Now for the fourth part, now that we've done this part, it's not that much harder. Or 4. Again, now we have the same cart, so we have x is equal to 0. We have our cart. This is now b of t at this edge of the cart. And we have the end of our domain L. And then we have our copper wire, and it's stationary over here, and it gets bundled up over there. So this is at some time 0. So at least, again, t 0.5 or something. Then at another time, this again, x equals 0 is going to be farther away. Same spool of copper. And then this is the end, x equal to L. So again, we can say this L2, this is L1. We say L1 is greater than L2. So the mass of the copper in the rest of the domain decreased. So that could be an indicator of a momentum change. So and again, this is b of t. So then we get the same type of integral. So we integrate over the rest of the domain, b of t to L. Oh, and in the same way over here, we're integrating from 0 to a of t. I don't remember if I mentioned that, but then we have the same type of equation. We have the density and the area times a velocity. But for this one, we don't need to do too much, because for this entire thing from b of t all the way towards L, the velocity in the copper is 0. So this entire section not moving. So that's 0, which means this is 0, which just turns this entire thing into 0. So that's just out of the picture. We don't even think about that. Okay, then E is pretty simple. The question is, are there any external forces that we need to consider? And if we look back at our photo, and this is the external to the inertial domain, not the accelerating domain or anything else. So every single, as you can see, the dotted line is representative of the inertial domain, but in every single thing that's like moving around here is all within that. So we're just not going to have just no external forces. Okay, no external forces. Then we get to F. And F basically tells us that F is what is the rate at which the x momentum leaves the left side of the control volume. Okay. So the first thing we need to look at is, so let's look at this at time is equal to 0, since we looked at the rest of stuff at that time as well. So get a rho w, aw, and then this is the same thing as problems in homework 7. You take the velocity of the column, because that's what's driving the momentum outflow. This times the normal vector, and then the same thing on this side, 0 t naught times the x vector, because we're looking in the x direction. And in this case, we know that the normal is the positive x, which is equal to x over here. So then this then simplifies to rho w a w b prime to column at 0 t 0 squared, because they're the same term. And then again, the same way as we did, same as CI, we get the same substitution. So I won't do that again, but the exact same thing. Cart minus, we're using the same, like that equation 4 from the question, from the given question stuff. And then we get this. So this is your velocity, this is your momentum outflow. Okay, then we're almost towards the end now. Now for G, this is, okay, on the right side of the domain, what is the mass inflow, I guess, since it's the copper, right? So we have copper, same thing. We take, again, we're not doing any pluses or minuses. We're letting all the dot products figure all that stuff out for us. So we take the velocity of the copper at L at the right side of the domain. And then we take velocity of the copper at LTO times the x, or in this case, the negative x, or no, this is still the x, sorry. The normal will come from the negative x. But we don't even need to think about that because we know that at the end of the domain, this is going to be 0, this is going to be 0, which just makes this entire thing 0. So we don't have to worry about that. And the last part, putting it all together. So in this one, we're basically just taking the left side, we're taking the momentum equation. So the momentum equation is d momentum of the x dt is equal to mass flux. So we got the mass flux. This is parts F comma G, and this is parts C comma D. So basically, if you take you add up all the terms on the from C and from D to the left side of the equation, and then you will just equate that to the mass flux. And the mass flux is just the water, which you derive in part F. And then you'll get this final equation. Yep, and that's the full problem. I hope that was useful to you guys. Yeah, this was really confusing for me as well when I first looked at it, but I'm hoping this helps.